So today we're going to talk about a very classical computer science problem. So the problem is known as um, set union sampling, set union sampling. Hello, welcome. Hey, you don't have to come. You know the topic already. Um, all right. So we will first define the problem, and then we will talk about how to solve it. Okay. So here we have a number of sets. Okay, so the sets are S1, S2, all the way to Sm. Okay, so here the value m can be arbitrarily large. Okay, so this m is not necessarily a constant. Now these sets, they may not be disjoint. Okay, in other words, you know, they could contain duplicate. They could contain common elements. Okay. Um, so as a useful example, you could think about S1 as the set of documents containing a particular keyword. Okay, so for example, the word computer. Okay, so you look at all the documents in your database, for example, the internet, and then this would be the list of documents, the IDs of those documents that contain the word computer. Okay, and likewise, you could have S2, for example, S2, and this would be the list of um, the list of documents containing, for example, science. Okay, the word science. Okay, you get the idea, right? So S1. So I was saying S1 would be, for example, the list of documents containing the word computer, and S2 would be the list of documents containing the word science, right? So this would be known. This is known as the inverted list, right? And clearly S1 and S2, they may not necessarily be disjoint, right? Because the same document can contain both keywords. So you can think about S1 to S1, S2, all the way to SM. You know, they are inverted lists of this kind. Okay, yeah. So we'll go into the application a little more after I have defined the problem. Okay. So anyhow, here we've got S1, S2 to SM as M sets that we care about. Okay. So we assume that we're able to do a bunch of operations on every set Si. Okay. So each Si allows you to do the following. Actually, there are three operations you can do. The first one is you get the size. Okay. So you want to get the size of Si. If you want to do that, you pay constant time, and then you get the size. All right, so that is the first operation. And then another operation is the so-called membership. Okay, membership, which basically says, well, given, say, an element, okay, tell me decide if, E is in Si, right? So for example, in this application I talked about, if Si is a list of IDs of documents, right? So for example, URLs of web pages, right? Now, basically the membership says, here is an ID. Does this Si contain this ID, right? Essentially, this is just a dictionary search, right? Okay, so this operation can be supported in constant time. Okay, so another thing that you can do. Now, the last one is called sampling. Okay, so here basically says you want to return, you want to get a random sample. Okay, so you want to draw an element from SI uniformly at random, okay? Uniformly at random, okay? So once again, think of this this inverted list example I've been saying. Hey, welcome. The room is not large enough, unfortunately. I'm sorry about that. So we just have to squeeze into this tiny room here. Well, fortunately, we do have enough chairs. um, yeah, sorry about that. Okay. Um, yeah. So I can recognize some familiar faces in my PhD course, though. So today's material is also in the course. Okay, so you don't get to learn new things. Okay, but I'll present it in a different way. Anyway, so I was talking about an application, right? So this is the inverted list application. So if you look at this SI here, this will be a list of documents containing a particular keyword, right? So when I say, hey, I want a sampling operation, that essentially says, okay, from all the IDs in this list, right, this SI, you want to return a random one. Is that okay? Yeah. So we assume that these three operations can be supported in constant time. Okay, constant time. Then what is the goal? So the goal is to draw an element from the union, so which is written here uniformly at random. Okay, so that is the problem. Okay, that is the problem. Okay. So for example, if I say S1 is the list of documents containing the word computer, okay, and S2 is the list of documents containing the word science. So basically, you want to get a random element among all the documents that contain either the word computer or science. All right, so that is the problem here. Okay, not intersecting. Okay, not intersecting. So this is union sampling. Okay, so in practice, you could imagine you have a lot of such kind of SIs, right? Because you have one I for every word in the dictionary, right? So for every different keyword, so you can have, you could have tens of thousands, such kind of inverted lists, right? So every list for a different keyword. And this M is really just the number of keywords that you care about. You see what I mean? M is not 10,000, okay? M could be like 2, for example, computer science, right? So you could imagine in the pre-processing stage, you have already built the necessary data structures to support these operations, right? Actually, a lot of such operations are trivial. Actually, all of them are trivial. Basically, size, that's very easy. Membership, that takes only a hash table. Sampling, that's basically an array, right? So, and then all these so-called inverted lists are pre-processed in this way, and then you are good for answering queries. Okay. So once again, I emphasize this M is really the number of keywords that you care about. Okay, it doesn't have to be it doesn't have to be the total number of keywords in the dictionary. Okay. So in general, as you can imagine, this is a very fundamental problem to database systems. You could imagine you could have a SQL query with where conditions. This where condition is disjunctive. Okay, disjunctive, saying, let's say A equal to 1 or B equal to 1 is what I'm saying. Saying like, for example, the occupation is professor, or the age is larger than 40. Some kind of um, statements like that. And suppose you are able to deal with each condition separately in terms of the sampling, right? So now the question is, how would you be able to get a uniform sample from the union of the results? Okay, good. So why is this problem non-trivial, first of all? Okay. Well, I think it would be easier to appreciate the problem if you imagine, if you start from an easy case where these sets are disjoint. Okay. So if these sets are disjoint, how would you solve this problem? Not too difficult, right? So especially if you still remember the stuff that I talked about before the break, okay, all those sampling tricks. And so what you can do is you can first sample at the set level, okay, and then you go into the set, right? So that this is a very, very typical two-step sampling strategy, right? So more specifically, you could first look at the sizes of all these M sets, right? So once again, I emphasize we're talking about the simple scenario where these sets are disjoint. Okay, so in that case, if you want to draw a uniform sample from the union of all these sets, right? Just ask yourself, what is the probability that the sample will come from S1? So clearly, the probability would be um, the size of S1 divided by the total size of all the sets, right? So what does that remind you? You know, that's weighted sampling, right? Weighted sampling. So what can we do about weighted sampling? You know, we have learned a powerful technique before the break. That was like several months back. The name is alias method, right? That alias method. So you're able to do that. In fact, what you have to do is you get the sizes of all these sets, and then you can. So that already takes you M dollars, right? And then you get the sizes, and then you can build an alias method on the fly over those sizes. Okay, after that, you can start drawing samples from the set. And then suppose at this level, you have somehow decided, you should sample from S1. That is the first step, right? You first draw at the set level. Let's say S1 is what you get. And then what will be the next step? That's simple, right? It's straightforward. So what you get is you go into S1 and then you want to do the sampling within S1, right? So with only the size and the sampling operations, you will be able to take a sample from the union in how much time? In M time, right? So the time is dominated by the time of building this alias method, right? By the way, if you want to do M time, um, well, what I'm trying to say is if you want to do better than M time, that would not be possible. Okay, why? Because in any case, you will have to at least take a look at each set. You see what I'm saying? Because there are M sets here, right? This is the first time you see them, right? Let's say. So you have to take a look at each set, right? Even just looking at the input, right? I get S1, S2 to SM, so I have M things there. Even just by looking at these M things, already takes you M time. Okay, so M is a lower bound on this problem, right? So anyway, as I said, if all these sets are disjoint, and then you can easily solve the problem using the size operation and also the sampling operation optimally in M time. Okay, good. Well, this method breaks when you have overlap among the sets. Okay. Think about it, right? Let's say there is some guy appearing in all these sets. Okay, so and every other element appears in only one set. Okay, and then you are essentially giving that element a very, very unfair share. Is what I'm saying, because that element has m occurrences versus just one occurrence for every other element. So that would not be a uniform sample. See what I'm saying? Okay, good. So let's see how to solve this problem. Okay, so I'm going to start with a sort of like a standard baseline solution, and this solution has been there for many years, for more than 10 years. It was the state of the art for a long time until it was recently improved. Okay, so the standard solution says the following. Well, let's just think about what I said before, right? So I said there's some guy that appears in all the sets. So this guy has a frequency of m. See what I mean? All right. Now let's just say that every other guy has a frequency of 1. All right. So let's think about a case like this, right? So how would you get a uniform sample in such a case, right? So let's get some intuition behind it, and then we will get to this baseline, right? So I'm asking you a very simple question. The question is, say there's some really hot item, okay, some hot document, and this document contains all the M keywords, all right? So this guy has a frequency of M, okay? But every other element or document appears in just one set. All right. So you have a situation like this. All right. So how would you get a uniform sample? Okay. So that is the question we are facing here. Okay. So I wouldn't say this is a difficult question, even if you don't see the solution immediately, maybe after 5 or 10 minutes, I'm sure everybody will be able to see it. So basically you have to do some sort of a correction after this is uniform sampling, the first step. All right. So imagine a situation like this. Say I got this special element, let's say E hot, right? So this E hot, just imagine, I create a pair for it, E hot 2, E hot M. You see what I'm saying? So this E hot appears in all the M sets, right? So let's imagine I have M pairs here just to sort of like separate those occurrences very, very explicitly, right? So it's like this E-hot appears M times, but every other element, this E1 appears in just one time in some set, and E2 appears in some set, and then let's say, some N minus one element. So in total, we have N distinct elements, right? So you have a situation like this, right? So let's say you sample from the whole, let's call this sort of like a universe. So this universe includes this E-hot M times. Okay, so basically it's the universe of occurrences. You see what I'm saying? All right, so this E-hot appears M times here. Say you take a uniform sample from the universe, right? So what is the probability? Let's say X. Okay, so X is, let's call this universe U. Okay, so this U is set, right? So this X is a random variable, actually uniformly random. Okay, uniform a random variable over U, right? So in this case, what is the probability for X to be E hot, right? So you can see the probability is precisely M over the size of U, right? Okay. On the other hand, the probability for every other guy, X E I for every other I, right? So this is precisely 1 over the size of U, right? So clearly, this is not all right because the probability of getting E hot is significantly larger than every other element, right? So when you have a situation like this, it's pretty standard to do a rejection step. Okay, rejection step, right? So I want the probability to be the same. So what am I going to do? Well, I will do the following, right? So this is the guy that gets a higher probability to be sampled, right? So I'm going to correct this in the following sense, right? So if you get E hot, and then I'm going to reject it most of the time. Okay, or equivalently, I'm going to accept it, just with a small probability. You see what I'm saying? So if I reject it, you don't get any sample. You have failed, essentially, all right? And that will be okay, as you'll see why later, okay? But I want to make sure that if I accept it, indeed I get a uniform sample, but this uniform sample is from the distinct union, right? So what do you do? Well, simple, right? So if we get E hot, and then we accept it with probability, how much? Just 1 over M. Okay, so this is the correction step, right? Or the acceptance step, I would say, the acceptance step, right? So this is what you do, and then you recalculate what is the probability for every element to get sample, right? So the probability of getting E hot will have to be the following, right? So E hat is returned, the probability that E hat is returned. So this is the probability of, X as defined before is E hat. First of all, you have to sort of like, it has to survive the preliminary round, right? So this X, right? So we have to get E hat. And then also, the X is accepted. E hat is accepted. That's what I mean. E hat accepted. All right. So what's the probability now? As you can see, this is M over U times 1 over M, right? So the probability is precisely 1 over U. Okay. On the other hand, if I get every other element and then I accept it immediately, there's no correction done. Okay. So if this is the case, and then you can see you are able to get a random element from the distinct union. Okay, why? Because every element is returned with probability 1 over U. You see what I'm saying? Okay, so this is the same for every single element. But where is the catch? Where is the catch? The catch is, you could fail now. You could fail. You see what I'm saying? So when you fail, what do you do in order to get a sample? Well, you repeat. Okay, so that is another standard trick in sampling, right? So if you fail, and then just repeat until you succeed. You see what I mean? When I say succeed, it means some guy really gets returned, right? So now that's the thing is, how many times do you have to repeat yourself? You see what I mean? That's the problem, right? So the probability of success is how much? The probability of success. Well, you can see every element gets returned with 1 over U probability, right? And you succeed when you return an element. You see what I'm saying? Okay. So, and all these, small successful events are disjoint. You see what I mean? This big successful event can be broken up into n smaller success events. You see what I mean? Why n? Because I have n distinct elements there, right? So what is the probability of each small success event? Well, it has to be precisely 1 over U because this is supposed to be a uniform random sample, right? So the probability of success, now you can see quite clearly, this is n times 1 over the size of U. Okay, so this is the success probability. So now if I ask you, what is the expected number of times that you have to repeat this in order to get a success, right? In order to succeed, the answer will be exactly the opposite. All right, so it will be U over N. Okay. So now in this special case, we're able to see that expected running time of the whole sampling algorithm is U divided by N. Okay, U divided by N. Okay. And this U divided by N, in this case would be this U divided by N, so that would be the expected running time. Okay, good. Well, let's generalize this idea so that we can get the baseline, okay? So now we will have a general situation, okay? So we will assume that the total number of elements is N, okay? So this is the size of the union, okay? The size of the union, all right? So this is the number of distinct elements you have in all those sets, right? So that's the size N. And also let's denote this big N as the size of the universe. Just to remember what a universe is, right? So you look at the total number of occurrences, right? So this is like one occurrence, but if there were multiple sets containing the same element, and then you have multiple occurrences for the element, right? So if you look at the universe has the total size of this. Okay. All right. So this is the universe. So once again, by universe, I want you to imagine something like this, right? So for every element in this set, and then you create a pair. You put together all the pairs. Okay, so that would be the universe. Okay, that will be the universe. So this is the size of the universe. So as you can see, the correspondence, right? So n here would be m plus n minus 1. Okay. So here, this n is really the total number of distinct elements you have. Okay, good. Now, what would be the baseline sampling algorithm generalizing this idea, right? So we sample from the universe, okay? Sample from the universe. Okay. Now we have to worry about what is the probability that a particular element gets sampled at this step, right? So let's say we get this sample X, okay? And we have to decide how to do the correction, right? So we have to analyze what is the probability that an element gets sampled. So let's say for each element, Y, all right? So if I want to calculate the probability for X being Y, would you be able to do it? Right. So this is my first question for you. Right. Okay. So you see, from the universe, every pair gets picked with the same probability. Okay. So that's 1 over big N. Right. So how many pairs does this element have? So that's essentially the question. Right. So you can see this element has as many pairs as the number of sets containing it, right? So this is, I would call degree of Y over X. Okay, so what is degree? So degree is the number of sets containing Y. Okay. All right, is that okay? All right, so now you know the probability for this Y to get sample is precisely like this, right? So how many sets contain you, right? So whenever you get confused, look at this simple scenario that I talked about, right? So you can see everything is generalized here. All right, so what else did I say? I said, okay, I want to, oh, divided by X, that's clearly a mistake. It should have been big N, right? Okay, good. Now, I want to correct this because clearly this is not good enough, right? Because we want to return a sample, and this sample is supposed to take every possible element with the same probability, right? So this is clearly different. So what do, right? And then what you do is you run an acceptance step. Accept E, accept X, okay, with probability 1 over degree of X. Okay. And then this is, I hope now it becomes fairly natural why you are doing this, right? So if I had shown you immediately this algorithm, there would be a lot of questions, but now I think it should be much more straightforward, right? So you want to take away the numerator here, right? Okay. All right, so if you failed, and then you simply repeat from the beginning. Okay, so this is the baseline algorithm. Okay, not a very trivial algorithm though. Okay, so first of all, we have to prove why this is correct, right? Why? So if we succeed here, okay, how do we prove that we are returning a uniform element? Okay, so I guess I will skip this step because I think it should have been pretty straightforward, right? So basically, you see, what's the probability for this Y to get returned in a success? Well, first of all, X will have to be Y, right? So that you can get considered. And then after that, you will survive the acceptance step with the probability of 1 over degree of E, right? So you will go through, overall, you will go through with the probability 1 over n. So 1 over n is the same for everybody, right? Okay, so what is the problem here? The problem is, okay, how many times do we have to do this, right? So with the experience from here, you know what you should be looking at, right? You should be looking at the success probability. Okay, so what's the probability of success? Then the probability of success, again, you think about this big success event broken up into small n of small success events, right? So each success event is on one distinct element. So each element will get returned with 1 over big N probability. So what's the probability of this success? It's just the sum of all those, the probabilities of all those disjoint events, right? So that's precisely N over big N. Okay. So how many times do you have to repeat this? So this means, in expectation, expected number of repeats is equivalent to big N of small n. Okay, so that's the algorithm, right? But there is a very important detail we have not touched upon, right? So how would you be able to implement this acceptance step? Okay, how would you be able to implement this acceptance step, right? So think about the operations that you are allowed to use, right? So you're allowed to use these 3 operations. Now I have a particular element for you, this yi, okay, yi. Now I want you to implement the acceptance step. Okay, so this is very important because you can see whatever you do there is going to go into the total running time because this is the framework, right? So the framework says, okay, you will be doing big N over small n repeats. But then every repeat would take you some time. You see what I'm saying? The time is precisely how much time you would need in order to implement the acceptance step. If your strategy is slow and then this is going to be big, and if you are fast, and then you get a faster algorithm. So this is a very, very crucial step here. Okay, good. So this is going to be the topic of the next 25 minutes. Okay. So now the question is, how much time do you need here? Okay, so let me first tell you a straightforward solution. All right, so how about I just get the value of degree first? I get the value of degree, and then I can easily do this in constant time, right? So how do I get the degree of X, right? So here I've got an element. I want to know how many sets contain this element, is what I'm saying. So one easy thing to do is to do this membership, right? So I simply pay M dollars, to each set. Do you have this element? Do you have this element, right? So I ask around, I ask all sets. So I pay M dollars, okay? So I can implement this acceptance step in M dollars, right? So in total, what is the expected number of dollars I pay? Well, now you know this is going to end up with, in total expected costs. This is equivalent to M times big N over N. Okay, so this is our first bound. Okay, our first bound. Okay. All right, do you have any questions so far? Okay, so this is our first bound. Okay. Well, this bound has been the state of the art, as I said, for a long time. And still remember what would be the best bound possible. The best bound is M, right? M. So ideally, we would like to do M, right? This big N, once again, big N is the total size of the universe, right? So I include all the occurrences, double counting them, that would be the size, that would be the total number of big N. However, the small n would be, this the number of distinct elements, right? So the ratio here is basically sort of like an average degree of each element. So I mean, on average, how many sets would contain an element, right? So that's the average degree, right? In the worst case, the average degree could be as high as M, you see what I'm saying? So that would be the case where every element appears in all the sets, right? So this big N over N does not really have a trivial bound. Basically a tight bound for this big N over N. Big N over small n would be M, is what I mean. So the only thing that you can claim about this algorithm in terms of M will be M squared. Okay, so this is essentially an M squared time algorithm. Well, M squared time is not too shabby. Okay, so once this is still related just to M, right? So at least you don't really need N time, for example. Okay, so that will be M squared. Okay. So now our goal is to reduce this all the way to M. Okay, so this is what we're going to do. All right. So I don't have much time. I still have 20 minutes left. Okay, I may not be able to give you all the gory details, but this is really just an excuse to introduce one powerful technique. Okay, one powerful technique in sampling. Okay, so let's go back to the crux of everything, right? So this is really the crux of everything, right? So this is the central issue, right? The issue is now I give you an element, say X. Well, X is a random variable. So when we are at this step, this random variable has been instantiated into a particular element, right? So I get to ask you this, right? So say I give you a particular element E, how would you implement this acceptance step, right? So you see, what we did before was to obtain the degree of E. So that was what we did, right? So that after that is after that is done, and then you can easily implement this acceptance step, right? So this becomes like generating a random value between 0 and 1 and see whether it's less than or equal to 1 over the degree, right? So that would be easy. But the interesting thing is that this is not necessary. This is just one viable way to implement this step. Okay, but nobody says to implement this step, you really need to get the degree of this E. Okay, so that's a very subtle difference that's going to make all the difference. Okay, it's a very subtle thing that's going to make all the difference. Okay. So next, I'm going to introduce a lemma. So the lemma says the following. So this is a separate lemma. Okay, so this is actually the most important message I want you to take away today. So let's say X. Let's think about this Y. Okay, so Y is a random variable in the domain from 1 to M. Okay, 1 to M. Okay. And suppose that I have another random variable. So this is a uniform random variable, a uniform random variable over 1 to M. Okay, so I have two random variables, and they are independent of each other. Okay, so the lemma says, okay, so what is the probability for X to be less than or equal to Y? Okay, so this is an unusual probability question. Okay, so what is this probability? It's an unusual question. It's not an easy question to answer because this Y is not fixed. Okay, if Y was fixed, and then this will be easy, right? So let's say if I say Y is just a value, a fixed value between 1 and M, then what is the probability? Everybody would say, hey, that's just Y over M, right? So that's very easy, right? But the tricky thing is Y is not fixed. Okay, so if that is the case, what would be the probability here, right? So this is a little bit unusual, right? Well, it turns out that you can prove this is the expectation of Y. divided by m. Well, this beautifully generalizes what we said about a fixed y, right? Because if y is fixed and then this expectation is just y itself, right? So this coincides with our understanding before, right? So y over m, right? But now the thing is, okay, what if y itself is randomized? So if that is the case, you can prove that this is the expectation of y divided by m. Okay. All right. So this is, well, there is a proof in my notes. So I'm not going to present the details. So once I have told you the result, what you are supposed to prove, I'm sure it's not too difficult to prove it. Okay. Anyway, in any case, the proof is quite elementary. So just take a look at the proof. Okay. Good. Well, and then let's go back to the acceptance step here, right? So this is the acceptance step here, right? Here. Okay. So think about, so I'm going to reproduce the acceptance step here, right? So the acceptance step, right? Accept with probability 1 over degree, okay, of this element x, right? So this element x at this point has become a concrete element, right? So this is the goal, right? So now I want you to put together, this tool and this goal, all right? So still remember what I said before, right? I said, okay, one way to do this is to get the value of degree x, but that will be expensive. Okay, in order to go from m squared to m, we'll have to do better than this. Okay, in fact, we'll have to do much better than this, which means we won't be able to know precisely what the degree is. Okay, there's no magic here. I'm not going to tell you a magic way to get the degree, faster than m. I don't know. I don't think that would be possible anyway. However, as I said, right, all I want is to have a probability. You know what I'm saying? What I want is to generate something with a probability. Okay, and as you can see, this lemma here, so I call this lemma probability through expectation, right? So this suggests there might be another way for you to generate this. This is basically, just like a very special coin toss. You see what I mean? It's essentially you want to generate a coin which comes up heads with this probability, right? That's it, right? Good. Very nice. Well, we're essentially at the doorstep of this solution already, okay? Now we just have to enter the room, okay? How? Well, think about it, right? So you see, this is something very easy to generate, right? A uniform random variable, right? So I can generate this without any dollars, right? Now remember, when you pay $1, you call one of those 3 operations that a set provides, right? But to generate this x, I can just generate it myself, right? I don't have to pay any dollar, right? Good. So what does that tell you? It tells you, hey, all you need is to give me a random variable, okay, with expectation of this, all right? Oh, sorry, I've been using this x twice, right? So let me change this x so that you can see things better, right? So let's say this z, and then z is less than or equal to y. Is that okay? Okay, so I can generate this z myself, right? So now suppose I can, so now the new goal here is to generate a random variable y such that the expectation of y is equivalent to what? Is equivalent to m over degree x. And they're all good. Okay. So let's see why, right? So once again, let's not get lost in the big picture, right? So here I got this x fixed to a particular element, okay? So you want to generate a coin, Okay, you want to toss a coin, right? This coin comes up heads with this probability. Okay, and you have this lemma to help you, right? So this lemma says, okay, as long as you can give me a y with this guarantee here. So this y says it's m over degree of x. Okay. Now this is currently the magic, all right? Because I haven't explained how to do this, but that's not very important. Because what is important is to demonstrate the power of this lemma here. Okay. So this is not so important. Actually, it's okay if you don't know how to do it, but I will explain it later. Okay. But the thing is, suppose that someone is able to give you this y already. Now the question here is how can you use this lemma to generate this coin? Okay. So that will be super easy because all you need to do after this y is available, you get it for free. You don't pay any dollars. How? Well, all you do is to generate a uniform random variable, and then you compare whether the z is less than or equal to this one. So once again, they say if something's important, you have to say it 3 times, right? I think I've said it twice now. This is the 3rd time. It's true that if you have the degree, and then you can implement this acceptance step. However, the opposite is not true, okay? The opposite is far from being true, okay? To do this acceptance step, it doesn't mean you have to do the degree. And I would say this situation comes up a lot in our research, okay? Oftentimes we want to generate a good coin, right? But so this is a wonderful example telling you, you can be more creative, right? Sometimes this heads probability could be difficult to decide, and then there's another way to do it. Okay, all right, cool. Well, the rest is pretty much just the standard details. All right, I still have 10 minutes, and let's see how much I can give you. So now the issue is, okay, I want to generate this y. Okay, you pay some dollars to generate this y. Okay, so here comes a very interesting question. Okay, you already have an element x. Okay, so I want you to generate a random variable. Okay, so that this random variable has expectation given by this. Okay, so what would you do? Okay. So once again, after someone has already posed the question to you, it will be probably just a matter of time for you to solve it, right? Because this will be a very concrete exercise, right? So I guess there's more than one way to do it, but one simple way is this, all right? So imagine this x, when you come to this x, right? So remember how you got this x in the first place. You sample from the universe. You see what I mean? Sample from the universe. The universe is like this, with the pairs. With the pairs, as you can see, with all these pairs, right? So you basically grab a pair. You see what I'm saying? You grab a pair. So you get this element together with a set ID. You see what I mean? That's what I mean, right? So you see you grab this pair and then you get this element, but you also get a set ID, right? Good. So now here, so we're looking at this x and together with a set ID, call it small s. Okay, so this is what you get at this point. Okay, very nice. Now, what I want you to do is this. Okay, so you still have S1, S2, all the way to S small s minus 1. Okay, and S small s plus 1. So I'm skipping, this is said, you know what, I will use a different one so that I don't have to say this S. Let's call it V, V, okay? So V minus 1 and V plus 1, okay? All the way to Sm, right? So I'm skipping this SV because you don't have to care about SV now. You know this SV contains this X, okay? But the thing you don't know about the other sets, okay? In order to calculate the precise value of this degree, you really have to ask everybody else, okay? But that's not the point here. The point is to generate something that that has this value, right? Sorry, generate a random variable whose expectation is this value. Okay, good. So the idea is, look, if this degree is large, and then there are a lot of sets that would contain this element, all right? Okay. And if this degree is small, and then, of course, you will probably have to spend more time. Okay. So now this is exactly why we're able to do this acceptance faster sometimes. Okay. If you don't utilize this property, you always pay m time, right? But the thing is, if this degree is large, there is a chance you don't have to pay m time. Okay. So this is precisely the place where this improvement comes. Okay. So this idea is this. Okay. So now you want to do the following. You want to see how many times you want to sample from this. And then you get another set containing this X. You see what I mean? So let me repeat, right? So imagine you do the following. I repeatedly sample from this, okay, until I get an element, I get a set that contains this X, okay? So now you can imagine if the degree is large, you will stop very soon, right? Okay, so in the best case, if all of them contain this element, and then you just one time, and then you stop, right? However, don't forget, but this idea, comes very close, but this idea doesn't work. Why? Because let's not forget that this number, z, it must come from this domain from 1 to m. All right. However, if you say, okay, you repeat or sample from this, and then potentially, you will have to sample more than m times before you can get a set that contains this element. So and therefore, you don't want to do this so-called sampling with replacement. All right, so sampling with replacement, sampling without replacement. I talked about this before the break. Okay, so you want to do sample without replacement, and that's the final solution. Okay, so the idea is this. Okay, so you want to repeat. Okay, so let's say you repeat. Okay, so you want to sample without replacement, sample without replacement, okay, from this set, okay, from S1 to Sm, except this SV, okay, you don't care about this SV now, right? You sample without replacement from it, okay. So until you get okay, sample without replacement, let's say you get some set here, let's call it T, okay, until T contains this X, okay. And then what will be the random variable Y? So the random variable will be how many times you have to, how many this WOR samples you have to get, right? So Y will be precisely, let's see, one would be, will be precisely the number of samples, number of WOR samples plus 1. Okay. So this is how we generate this Y. Okay. So I don't have time to really go into full-blown analysis, but let's get some intuition. How come the expectation of Y should be this value? Okay. So let's consider some extreme cases, right? So let's say the degree of X is just 1, which means just SV contains this element, and these guys, none of these guys contains these elements, right? So if that is the case, if you keep doing sampling without replacement, so how many repeats do you have to, how many samples do you have to get? Well, you have to get all of them, because you'll never see a set containing this element, right? So here, this number of WR samples will be precisely m minus 1. And then plus 1, that's exactly what I promised. Okay, now consider another extreme. Say if if the degree is, say, the degree is m. If the degree is m, and then how many samples do you need here? You will need, wait a minute, if the number of degrees is m, so expectation should be 1. Then what is wrong? Let me see if I got. Must be m minus 1, sample without replacement. If the samples we get, okay. Unfortunately, the sampling algorithm is slightly more complicated than what I just said. Okay. So let me have the algorithm in my lecture notes, right? So it says the following. So you first sample. Okay, let's be very precise. Okay, so here, let's say in the beginning you have y being 0. So you have y being 0 here. Okay, and then you sample. Okay, so if y is in t, and then you return, you don't do anything else. Okay, else you increase this. This is x. Okay, you return y. Okay, you return. You return. So let's say you got this f here. Sorry about that. So f, okay. So you return f, otherwise you increase f by 1. Okay, so this is the algorithm. Okay. So so this is not completely the same as what I said, because this counting is a little bit different. All right, so it's not necessarily how many samples you have. Okay, so it says the following: you in the beginning you maintain. You said, I mean, the whole algorithm is going to maintain this f. In the beginning, you set it to 0. Okay, and then you take a sample. If this set, okay, from here, right, contains this element x, and then you return the current f. Otherwise, you increase it by 1. Okay, so this is what it's supposed to do. Okay. All right, now finally, this y will be f plus 1, right? So this is not precisely the number of samples you get, right? Because if you really get a hit, and then you do not count the last set, is what I'm saying. This is the subtle difference. Anyway, so let's quickly look at some extreme, some representative cases, right? So let's say the degree is just 1. As I said, none of these guys will contain this x, and therefore this f is definitely going to be m minus 1, right? So m minus 1 plus 1, so that's just m. So this is as promised, right? Now, on the other hand, let's say the degree of x is m, right? So the expectation is supposed to be 1, right? But what happens here? So you see f equal to 0, and then you sample some guy, and immediately you see that it's contained there, and therefore you return this 0. And therefore this y is precisely 1, okay? So in general, let's say the degree is sort of like m over 2, okay? Something like that, right? So what is the probability how many samples do you need here, right? So you can see roughly half of them will contain your element, right? So this will be roughly 1. You see, I mean, you when you return is roughly 1, right? Because you take 2 samples, but f is increased only once, right? So, and then in the end, y will be 2, right? Okay, I hope this gives you the strong intuition that in general it will be proportional to actually inversely proportional to how many sets contain. Okay, all right. So that's all the time I have to wrap up quickly. So if you do this, and then you can achieve the following, right? So as you can see, the time of generating this random variable really depends on how many samples you do take here, because you pay only from here. Is what I mean. You pay only from here, right? So because you have to check this membership, right? So this is the only thing that you pay. And then how many dollars do you pay? Well, you pay an amount of dollar that is proportional to this. Okay. So let's compare this to the baseline solution. The baseline says I always do M dollars. Okay. But here you do fewer dollars if this X has a large degree. Okay. Okay, now let's try to imagine the following, right? So if this X has a large degree, I mean, some elements have a large degree, some elements have small degrees, right? So if this is the case, why do we game in expectation, right? So the idea is this: if an X has a large degree, and then I pay very little here, although this element will get sampled more often because it has a large degree, right? So it will get sampled from the universe more often than other elements, right? On the other hand, if an element has a small degree, then of course I will pay more. But the thing is, wait, this element also has a small probability to get sampled from the universe in the first place. You see what I'm saying? And therefore, overall, you do benefit from this degree. And precisely how much? Well, this is analyzed in the lecture notes. These are the details, right? But not too difficult if you go through the details, and then you will see precisely we're able to do how much better than M, precisely small n over big N. Okay, if you still remember this N and M, right? So this N and M says this is small n, this is universe size big N, this is a number of distinct elements, right? So we're able to do small n over big N. So exactly we get faster than the baseline solution by this factor here. Okay, so that's how we reduce the time to n in expectation. Okay. All right. So I overran for 2 minutes. Sorry about that. Okay, so that's everything I have for today. Okay, so I hope to see you next week. Okay. All right. Bye. Hey, thank you. Thank you, guys.